right, so we're going to do a fun little example problem looking at specific heat and latent heat and summertime barbecues. So let's imagine that you're having a barbecue and you want to put a 1 kilogram chunk of ice into a already chilled bowl of lemonade. And we're gonna pretend this is an isolated system and we're not gonna lose any heat to the environment, and we can just look at the transfer of energy between the ice and this cold lemonade. The question is, does the ice melt? Will the ice melt all the way? Will we have icy lemonade kind of maintained in a nice lovely amount of ice? What will the state be of our system? So what do we have to think about? Well, a couple of things are going on here, right? First, we're going to cool down that lemonade. So we're going to remove heat from the lemonade, and that heat's going to be transferred to warming the ice and melting the ice, okay? So we have to think about what kind of energy is needed to do those things, and do I have that energy available? And if so, great. If not, what happens? All right, so let's talk about that. So the first thing is, let's look at how much energy it takes to cool the lemonade. So how much energy, how much heat to cool the lemonade? All right, that's our first question. How much heat to cool the lemonade? Well, the lemonade is in liquid form and staying in liquid form, right? We're just cooling it from its 10 degrees Celsius down to when we would start to freeze it at 0 degrees. So because we are in a steady phase, we will use this specific heat relationship that we learned about. So Q, the amount of heat, related to the mass times the specific heat, and we're going to use water, where lemonade and water are pretty much close enough, times our change in temperature that we're trying to achieve. So we have 4.5 kilograms of lemonade. The specific heat of water is 4186 joules per kilogram degrees. And we are converting that from 10 degrees to 0. So that's a 10 degree temperature change. How much energy is going to be removed for that 10 degree temperature change? And if we, oops, I'm the wrong solution up. If we look at that total amount to lower the temperature, it is going to take 180,370 joules. And I'm just going to leave all of our integers up right now. So that's how much energy I have to remove, or that will be removed from the lemonade to decrease its temperature down to 0 degrees. Okay. So what else do I need to know? Well, I need to know if that's enough energy to change the temperature of the ice. So that's the first thing we're going to check. Is this enough energy to change the temperature of the ice? We know we're going to get to thermal equilibrium, right? So is this enough energy to change the temperature of ice? All right, well, if I'm just changing the temperature of ice, not changing any phases, we're going to use that same relationship for heat's relationship to changing temperature. Within a phase, I have 1 kilogram of ice. The specific heat of ice is 2100 joules per kilogram degrees C. And we are changing this from 0 degrees to 5 degrees. Back that up, from negative 5 degrees to 0. So there's a temperature change of 5 degrees as we start to warm the ice. And if we were able to do that, that would require 10,500 joules of energy. So I have enough energy that I would convert from cooling the lemonade to heat up the ice. So that's good. How much energy is it going to take to melt the ice? Remember, we're trying to decide if the ice is going to melt or not. So if the ice were going to melt, so heat to melt, what would that require? Well, now we're in a phase change, right? So we have to use the latent heat relationship. And we're going from ice to water, so we're going to look at the latent heat of fusion. All right, so I have 1 kilogram of ice The latent heat of fusion is 3.33 times 10 to the 5th joules. And that joules, but joules per kilogram. And then the total, therefore, amount of ice that we need is 3, joules of energy to melt all the ice. Well, that's more than I would have just from cooling the lemonade down to that ice phase. And so we end up with the ice not all the way melting. I don't have enough energy to melt all of the ices, and these are going to reach an equilibrium state, and it's going to be a mixture of water and ice, which is good. The ice isn't going to melt. We're going to have nice, cool lemonade at 0 degrees. So that's going to be lovely for our backyard barbecue. Now, if your backyard barbecues are anything like my backyard barbecues, somebody doesn't do their job. It's usually my husband. And, well, that means we end up with this problem. Instead of the lemonade being at the cool 10 degrees, he took it out of the fridge too early, and it's at 20 degrees. How does that change? What does that change? Will the ice melt this time? And if it does, is my lemonade going to be cool enough to serve to my guests? Well, let's see what changes in our problem. Same kind of process. First, we got to see if we have enough, right? So now instead of cooling the lemonade from 10 degrees down to 0 degrees, we have to cool it from 20 degrees down to 0 degrees. So how much does that change the amount of energy that we are going to be using to cool the lemonade? Well, do we have enough, essentially? So we're going to use the same relationship because we are, again, in a single phase. And we still have 4.5 grams of lemonade. It still has a specific heat of 4186. And now we're going to convert it, or sorry, not convert it, but we're going to try to decrease its temperature by 20 degrees. So our change in temperature is 20 degrees. So this is a doubling of the amount of heat that's needed. And instead, we need 376,740 joules of energy would be available to do this process, to melt the ice. So does the ice melt? Well, if I add these two up, we see that in order to completely melt the ice, it would take a total of 343. So I'm adding these two together, 500 joules to melt the ice. And I actually would have more joules than that to cool the lemonade. So now we're going to continue to heat this liquid until these are at thermal equilibrium. So my ice is going to melt. The question is it still going to be refreshing? What will be the temperature that this reaches equilibrium? Right? Will it be refreshing? So how do we figure that out? Okay, that's kind of a different problem. So the idea now is not totally different, but a little different. How much heat is changed such that we get to a common temperature? So I'm going to erase this and we're going to ask this. This allows us now to kind of look at the idea that the total heat, the sum of all the heat transferring going on is going to be 0. Remember, we don't gain or lose any heat. So all the heat that's lost from the lemonade is going to be gained by the ice. So what is the processes that are going to be happening? We've already talked about some of them. We're kind of going to start over because it's going to be all of these heats, processes that are going to contribute to the total heat being 0, the amount gained equaling the amount lost. So let's write those out individually. They're going to look similar for some, and make sure that we understand the process. So we know that we are going to, because we have more heat that it would take to bring the lemonade down to 0, and we need to melt the ice, we know we have some heat to play with, essentially, that is going to result in heating the water from the melted ice until the lemonade and the ice, now melted as water, reach thermal equilibrium, okay? So it changes our problem slightly, but first we had to check if we had the heat to spare, so to speak. Okay, so we had to do that check first, and now we got to figure out what's equilibrium. So, like we did with our previous equilibrium problem, we first looked at this. Let's go through the different heats that are going to be involved in this scenario, the total heat that we're going to deal with. First of all, we are going to reduce the temperature of the lemonade. Now, we have no idea what temperature we're going to reduce to. We know that it's going to be above 0 because we've used a bunch of energy to melt the ice, raise the temperature of the ice, melt the ice, and now we're going to heat the melted ice to thermal equilibrium with the lemonade. So we don't know the temperature we're getting to, but we know we're going to reduce it. Okay, so that's one heat element. We are going to increase the temperature of the ice. You might think, why'd you erase that? We already had that. That's okay. We want to kind of start this one over so we really understand it. Increase the temperature of the ice. We're going to melt the ice. Okay? And then we're going to heat the melted ice, aka water, to our final temp. Okay, so we're reducing the temperature of the lemonade to the final temp. We have to increase the temperature of the ice, melt the ice, and then increase the temperature of the melted ice to our final temperature. And that final temperature is where we'll be at thermal equilibrium. And again, my question is that cool enough for my guests? All right, let's try it. So we have to consider all of these pieces. So I'm going to put them in those relationships of Q, right? Our heat. So we have Q1 plus Q2 plus Q3 plus Q4 all equals 0. Okay? The sum of the heat has to equal 0. Q1, reducing the temperature of the lemonade. All right, so Q1, I'm going to put these over here for a minute. I'll erase this in a little bit. Actually, let's do it this way. I'll erase them as we go. So Q1, we are only in liquid phase, so we are going to use our specific heat relationship. The mass of the lemonade was, what was the mass of the lemonade? 4.5 kilograms. The specific heat, 4186. And our change in temperature, well, it's whatever our final temperature is minus what we start at, which is 20 degrees. Okay? So this is Q1. I'm going to simplify it. And we end up with, oops. Oh boy, I'm losing my spot here. The mass of the water, that's the ice. We end up with 18, I don't have a calculator in front of me, 837 times, that's 4.5 times 4186, times the final temperature, minus 4.5 times 4186 times negative 20, which is 376,740. Ooh, that looks familiar because that was what it was to change it by 20 degrees. So that's good. That's good. All right, I have the right numbers. So that's for Q1. Q2 is to increase the temperature of the ice. Again, we're in steady phase, so that's going to be MC delta T. The mass of the ice is 1 kilogram. The specific heat of ice, remember, is 2100. And we are raising that temperature from -10 to 0. And so that is 10. And that is the same number we calculated before, 10,500 joules. Okay, so same calculation as before. Q3 is to melt the ice. That, remember, is a phase change, so we're going to use ML, and we're going to use the latent heat of fusion because we are going from a liquid solid to a liquid. And we calculated this last time also. Oops, there's only 1 kilogram of ice. So we have 1 kilogram of ice times 3.33 times 10 to the 5th. We end up with 333,000 joules to convert our ice to a liquid. And the final Q4 is heating our melted ice to whatever the final temperature is. So there's no change in phase, so we're going to use MC delta T. We have, and make sure I'm still on screen. Okay, I'm going to go across this time. We have 1 kilogram of water. The specific heat of water as a liquid is 4186. And T final minus 0, because we're at 0 degrees once everything is melted. And so that is 4186 T final. All right, so each amount of heat individually, and now we're going to put them all up here in this equation as I erase them. So we have, for Q1, we have 18837 times our final temperature minus 376740 plus 10,500 plus 333,000 plus 4186 T final, and that has to equal 0. Okay, I'm gonna erase these so I give myself a little room. So I did the individuals kind of drawn out for you to make it clear. And now we're going to solve for our final temperature. All right. So we have our, oops, I did that again. Oop. All right. I want to get all the numbers right. So we're going to add up all of our totals, and we end up with minus 33240. So I add 333,000 plus 10,500 minus 376,340. We get 33,240 plus my 2 T's, which is 23,023, and that equals 0. Oh, T final. Move T final to the other side, or move that 33 to the other side. We have 23,023 equals 33,240. I forgot the T. T final. And T final equals 1.4 degrees, which is still pretty chilly lemonade. So I think my guess will be all right. There'll be no ice in it, but it'll be a nice refreshing 1 degree. Okay, lots of steps. It's all about breaking it all down. What is happening? What are the possible things that heat is going to be used for? keeping those separate, recognizing when it's a phase change versus when it's in a steady state to know which of the heat relationships that we need to apply. Of course, paying attention to whether we're using the latent heat of fusion or vaporization, and then remembering that the total heat, all the heat in and all the heat out, has to match. All right, good job, and enjoy your barbecue.